So last time we introduced curvature of connection on a fiber bundle. So if I have a fiber bundle E over X, and I have choice of horizontal subbundle, so connection. Then I have actually two maps. One is projection, fiber-wise projection to vertical subbundle, and the other one is fiber-wise projection to horizontal. So this is projection along horizontal, this is projection along vertical. And then both of these maps induce also maps that are from sections on TE. Well, say K gives me map from sections of TE to sections of VE, and H also gives a similar map to sections of HE. So basically we just take section means like a bunch of vectors, and so at each fiber we just project to the corresponding subspace. That's it. And also we introduced this two form, omega H, we denoted it by omega H. So this is its two vector fields on E, and gives another vector field on E. Right. And so the definition is that omega H of two vector fields is negative K of the commutator of H of psi and H of eta. Yes. So that's the definition, and we call it curvature to form. And it is really to form on E, right, with values in here. Okay, so now we need so definition, just terminology rather, is that connection HE is called flat if it has no curvature. So this to form is 0. And then we have the following theorem, is that connection is flat, HE is flat, if and only if for any choice of point X in X and its lift P right in E, so P lives in EX, there exists open neighborhood of x. So our point x lives inside. This is open. And a section, so it's a local section of E. So this is belongs to gamma of E restricted to U. Such that, well, first of all, value of S at X is exactly our chosen point P. And also covariant derivative of S with respect to V equals 0 for any V in, well, it's vector field on U. So that's the statement. So my curvature is 0 means that I locally have constant sections, and like at each point actually. So that's it. So let's prove it. But I mean, we will just deduce this statement from Frobenius theorem, which, well, so honestly speaking, we should prove, but we don't have time for that. It's like more classic, like, I don't know, more standard. You can find it anywhere. So I will just state it, and we will see why this is a consequence of Frobenius theorem. Okay, so first, proof. Okay, first let us prove if part. So if I have such a section, then my curvature is 0. Right. So let me fix such section. So my I have 2 points. I have point X. I have P. Right. I have U, which contains so all that stuff that I have in the theorem. I fix. So such U exists, and section S is from gamma of E U. And I know that nabla of S is 0. Then well, I can take image S of U, right, so S of U. This is actually, so I claim that this is a submanifold of E, right? Well, this should be clear. And then then let me take any, so for any y, that's a point in U. Well, tangent space of this submanifold at point S of y, right? Well, it lives inside, of course. So because of this condition, right? So this lives inside H E. Well, at what point? At point S of y again, right? Just because, well, what I'm doing. So tangent vectors are exactly the ds of tangent vectors at a point y at x, right? And since this condition, I know that they all belong to horizontal subbundle. Okay, then, but actually I can write the equality sign here, right? Because, I have that pi, S composed with pi is identity on U, right? I can take differential of this, so ds should have rank, right? Should have rank dimension of x, right? Otherwise, this would not happen. So ds has rank n, which is dimension of x. So therefore, dimension of this is equals to dimension of this. So actually, this tangent space is of course the same as just fiber of HE and point S of Y. Okay, then let me take, so what I am looking at? I'm looking at this thing, right? I would like to prove that this is, actually that this thing is horizontal. What's in here? Because then I project it to vertical, along horizontal, I get 0. Okay. So let me maybe rewrite this guy here, so it stays on the board. H of psi, H of eta. Okay, so I take any two vectors xi and eta. So these are vector fields on E. And so then I take H of psi, restrict, well, at my point S of Y. And also, well, the same thing with my eta. So they both actually belong to, of course, horizontal, well, the fiber of horizontal bundles, and because of this, actually to the tangent space of this submanifold that we have, right? So actually, let me write it like this: T S of Y of S of U. So therefore, it actually means that if I take these things and restrict it to submanifold S of U, so this belong to vector fields of S of U. So this give me vector fields on my submanifold. No, just because of this. Okay, and so therefore I can take commutator of this vector fields, and there still be a vector field on this submanifold, of course, right? So, but actually taking a commutator, so I can take commutator. But this is like, it's just the same as taking first commutator inside the bigger manifold, and then restrict it to submanifold. It's just a property of vector fields of submanifold. You can compute commutators like this. And then I know that this guys live, so this is inside vector fields of S of u. And so therefore this guy as well. And so therefore commutator of these two things is actually horizontal. And so therefore we have that curvature is 0. All right. So h of psi, h of eta well, at our point P, which was S of x, is inside HP of E. So therefore, curvature, if I take K of it, is 0. So omega H of psi eta at point P is 0. Now this is for any chosen P, so this is identically 0. And this, so this, we don't even need any Frobenius theorem for if part, because this way it's easy. Okay, so what about the other way? So maybe let me leave theorem here. So the other way goes, so only if part. Well, suppose that curvature is 0. Then if I take two vector fields, which are actually inside my, so these are two sections of the horizontal bundle, then I can compute commutator, and this will belong to, again, to gamma of HE, just because curvature is 0. So this should be horizontal. But then we will use Frobenius theorem that I'm going to state right now. Theorem. Okay, let M be some manifold. And let me consider this so-called distribution. So it's some bundle inside Tm. So this is sub-bundle. So such thing is called distribution. So this is vector sub-bundle. All right, and then one might wonder if there exists submanifold such that at each point each tangent space is given by the value of D at this point. And the answer is that it does not happen every time, but it happens under some conditions. So if, what is this condition? So exactly what we have here. If I compute commutator. So if for any psi and eta, which are sections of D, commutator of psi and eta is inside is also section of D, then D, so this is called D is involutive, right? So then D is locally integrable. That is for any point x, like I don't know, x in M, there exists, of course, submanifold n of M. Well, of course, x should be inside N, such that for any y in N, T y n is exactly dy dy. This is fiber of this bundle. Okay, well, this is useful theorem, but rather than spending time proving it, let's just use it in this. So, okay, we have HE, which is distribution, and if our curvature is 0, this distribution is involutive, and so therefore it's by Frobenius theorem it's integrable. So therefore so by Frobenius theorem, for any P in E, there exists submanifold N of E, so this is submanifold, such that N Q, well, T Q N, right, is exactly H Q E for any Q in N. Okay, so we can actually shrink this submanifold actually. So we need to recall that. So I have this projection map, right, pi from E to X, and then if I take d pi and restrict it, well, at our point P, and restrict it to HPE, so this becomes, so this is isomorphism. So therefore pi restricted to n locally around point P is the diffeomorphism. Well, locally around any point actually, but let us concentrate on the point P, right? So there exists some maybe smaller neighborhood and well, submanifold and tilde, and P is inside, so submanifold of E such that n tilde, well, such that pi restricted to n tilde is well, it's diffeomorphism to some u. Is diffeo for some u. So let us just now take this pi restricted to n tilde and take its inverse, and this will be exactly our section. Right? So we need section such that covariant derivative in any direction is 0. All right. And this section goes through any arbitrary chosen point. So I have that. Define S from U to n tilde to be S equals pi restricted to n tilde inverse. So this is section, and well, the corresponding submanifold is such that its tangent spaces belong to horizontal subbundle. So namely, actually, I can do the following. Can write the following, that d y s of v of y, right? So here y is any point in U, v is any vector field on U, right? Then this is this actually is, of course, just by construction, tangent space of S of y of n tilde. But this thing is the same as the horizontal, the fiber of horizontal bundle. And so therefore, covariant derivative of S is 0. Because it really measures the projection to the vertical bundle of this thing. Ага.
А можете дать какую-то интуитивную идею, почему нужно область, в которой можно построить такое векторное пространство?
Я могу дать интуитивную идею, почему, если кривизна не нулевая, то тогда нельзя такого сделать.
Если, кстати, прямо говорить, что у тебя многообразие плоское, если есть поле, которое как бы постоянно сфера, ты как бы движешься вот так, ну, ты движешься вот так, вот так.
Да-да-да, вот давайте это нарисуем. Значит, okay. This is rather illustration to my next statement, is that if my curvature is 0, then my parallel translation around any loop is should be identity, right? But let us give this picture right now. So we proved theorem first of all. So let me erase this. Значит, если у нас, if we have a sphere, right? So this is like a standard example. I can, for example, well, I can like make like a very small u, but usually it's taken that. Let me take this point and then turn 90 degrees, then go up, and then return here. Right, so if I take a vector like this, so parallel translation, that it just goes like on the same angle to this geodesic. That's what the parallel translation is here. So I parallel translate it to here, then I move it to here, right? This will be this vector, right? Then I move it to here, and this will be this vector. So when I go around like this, I turn 90 degrees. So if I make this, so in here, so this is my U. So on U I cannot have a flat section, so to say. So on U, so I take my P in this theorem is this vector that I chose, right? So I am talking about E, which is tangent bundle on a sphere, right? My P is this vector that I chose here, right? I don't know, this V. And so suppose that my curvature is 0. Then I can have on this U, actually, well, I can add small enough, so then just this is more illustrative, right? Because, well, if it's small, then the angle of rotation will be just smaller. But it will still be like not 90 degrees, but maybe smaller, if I go like a smaller triangle. Anyways, so if I'm saying that on U I don't have section which is flat, because if I had, then the values of this vector as I parallel translated here would be just values of this section, right? Because this condition says basically that if I move in any direction, I do like a parallel translate.
Сейчас, она же должна не заданная U существовать, она просто какая-то должна существовать для P.
Ну, она какая-то, еще раз, тут никакая не существует, вы можете как-то уменьшать там этот U, просто это наиболее, ну, удобно так представлять, да. Тут он как бы развернулся на 90 градусов, прямо вот видно. Вот. Значит, ну вот, если бы у меня существовало, то существовало бы такое, вот, и я бы просто вот все вот эти вектора, которые я здесь делаю, они были бы значениями вот этой S в этих точках X. Ну и понятно, что если я по одной и той же, по одному и тому же сечению хожу, то когда я вернусь в другую точку, у меня должно быть как бы то же самое значение, оно здесь не происходит. Okay. So this is, yeah. So this is an illustration rather to next statement. Is that so corollary one, we'll have more of them, connection is flat if and only if for any x, from x there exists some open neighborhood of x that contains this point such that parallel translation along any loop gamma in U is identity. Okay, so let's see how it follows from theorem before. Proof. Again, so first let us prove if part, which is if I have this condition that parallel translation locally is around loop is identity, then my connection is flat. So this so okay, we need to take well x, so fix some point x in my manifold, and suppose that u is neighborhood like in the corollary. Like above. Okay, then I would just like to define S section, and also I need to fix some point P in the fiber. Right, and so I need to actually construct section which is flat section going through P, then my curvature is 0 by previous theorem, right? So how do I do this? So I define S that lives in gamma of E of U by, well, we can take actually U to be connected, of course. And then any point in U, I just connect to X by any path. Doesn't really matter, because my translational log any loop in U is identity, so I'm going to use it, right? So I take how do I want to write this down? So for any, so such that for any y from U, S of, well, first of all, S of X is P, and S of Y is parallel translation of P along any path from X to Y. Well, since any loop gives me identity, doesn't really S of Y doesn't really depend on path, and so this is well defined. Right, but then I claim that so if I take any V vector field of X, I need to see that this is 0, right? And at any point in U, at any point Y well, this is V in vec X or V in vec U in this case. Doesn't really matter, I can restrict it. So Y is in U. So I need to see this. Well, I just take curve. So just consider curve from x to y, right, such that, well, my gamma, so meaning that, okay, this is curve from like A, B to U, right? It's inside U, and gamma of A is X, gamma of B is Y. So I just want gamma prime at B to be V of B. I have a lot of freedom to do so. So if I take 2 points and a vector at this point, I can of course construct a curve that goes from this point in this direction and then connect it to this point, right? But then this S, well, this is gamma of B is Y, right? And so I just have that S of Y is parallel translation of S, well, it's just parallel with respect to gamma, this gamma that I chosen. So therefore it means that, so just S of gamma of T. I should write like this, right? So this is like a curve up above, right? Since my nabla of S is 0, so therefore its nabla of gamma prime of this is also 0, of S of gamma prime. So therefore, this is parallel with respect to gamma. Well, so therefore, nabla, yes, so therefore nabla V of S at this point, Y that I chose, is just 0. So I say that, okay, this is parallel because this is 0, but this is, no, this is not true. So this is parallel because we just defined S like this, right? So this is just by definition of S. And so therefore, so this is parallel, hence by definition of parallel is just like that, and that's it.
Мы до этого хотели определить S как, при помощи любого пути, а тут
Да.
фиксируем.
Ну, мы фиксируем путь, потому что я хочу, чтобы у меня для любого V вот это выполнилось.
То есть мы в итоге хотим, чтобы вот на этом пути
Да.
S от гамма от N как раз таки задаем его так, чтобы оно было параллельно.
Нет, я его задаю так, что я беру как бы любую точку y в u, вот, или беру любой вектор v. Вот мне нужно, ну, y и v здесь произвольные. Вот, я должен показать, что вот это 0. Вот, ну давайте, кривая в данном случае это вспомогательная вещь. Это значит что-то, что как бы соединяет вот x и y так, чтобы оно выходило под углом вот заданный вот этим v. Вот, это все, что мне от нее нужно. Ну и тогда просто, так как вот просто по построению вот этот просто параллельное семейство относительно гамма, по построению S. Потому что S так построено, что S от Y это параллельно для любой кривой. Ну, в частности, для этой. А значит, просто по определению, что такое параллельное семейство, это значит вот это. Ну, потому что вот это как бы...
Но это в любой точке выполняется, потому что
Да.
вместо должен написать гамма-штрих.
Ну да. Okay. So, right. What else? So this is this direction. The other direction. So only if part. Well, suppose that curvature is 0. Then, well, by theorem, right, we have for any x, there p from Ex, there exists S, well, some U, right, and S, which is section, local section around X, so gamma E restricted to U, such that, well, curvature, well, such that nabla of S is 0. So this section is flat. Right? Okay, let us take this section and let us take a loop in this U. So gamma, this is a loop in U, right? So let me just take gamma tilde of T. This is parallel. Just define it to be parallel with respect to gamma, such that gamma tilde of 0 is, well, loop in U, I should specify that goes like from X to X, right? So gamma of 0 is X, such that gamma tilde of 0 is P. So I take P and parallel translate it along this loop. Right. Well then, again, because of this condition, my gamma tilde of T is exactly S of gamma of T. So parallel translate means that, well, I take a curve, right, such that at each point nabla gamma prime of gamma tilde prime is 0. So if I take this and plug into this equation, I will get 0, just because S is flat. So therefore we have this, and since gamma of 0, well, gamma of 0 is of X, and say gamma of 1 is X. So it's a loop. Since gamma of 0 is equals gamma of 1, and this is section, which is well defined, so therefore it means that gamma tilde of 0 equals gamma tilde of 1. And so therefore parallel translation is identity. Right? Since this equals, therefore value of S equals, and so therefore this. And we are done. Okay, this is one thing that we wanted to observe. Another thing is that actually flat as a connection in case of if it's a linear connection, means that it's locally trivial. This we can also obtain from this theorem. So HE, so let HE, again, so let pi from E to V to X be vector bundle. And let HE be linear connection. And so therefore it means that it's just our connection in the old definition. Right, so then HE is flat if and only if for any x from x, well, locally, there exists chart right around x with a basis of gamma of E restricted to U. Well, basis, I mean C infinity of U basis. So over C infinity of U. Such that the corresponding Christoffel symbols are 0. So it means that if connection is flat, so like symbolically, if and only if connection is just D locally. So this is like, it means it's locally trivial connection. Okay, let's see how we can deduce that. Again, we have two directions. Think only if part is maybe easier here, right? So if it's flat, then it's locally trivial. So suppose HE is flat, then if, okay, let me fix some x and let P1 PR be a basis in the fiber. So fiber is now is linear space, I can fix a basis. And then, so there, I can also fix U. Well, yes, okay. So then by theorem, since my connection is flat, I can find U neighborhood of my point X, right? Well, and I can find S1, so I can find like R sections. So these are sections of gamma of E restricted to U. Such that my nabla of Si is 0, well, and Si of X is Pi, right? Well, theorem says for any point, well, let me fix R, which forms a basis, and for them, construct like R sections. R flat sections. So then, well, so linear independence is kind of open condition. So I can actually so my Si are linearly dependent at these points, right? So therefore they're linearly independent around this point as well, right? So therefore I can actually assume. I can assume that my U is small enough such that S1, S1 of Y, SR of Y are linearly independent for any Y from U. And also I can assume that U is small enough so that I have coordinates on U, right? Then by star, corresponding Christoffel symbols are 0, right? Well, how do I obtain? I take locally basis, act by connection, and decompose it. So decomposition is just zeros. The other way, so this was only if part. So I go the other way. So what am I proving? I'm proving if it's locally trivial, then it is flat. So basically I need, again, to use this theorem and construct for any P, construct a locally section which is flat. Right, well, that's clear how you can do this. You just take, some basis, basis like in the condition of the corollary. So take this, so basis of gamma of E restricted to U for some U, right, such that Christoffel symbols are 0. Then let me take any P. So let me take any X from U. Let me take any P from EX. So then I can actually take this P and decompose it with some coefficients Vi in this basis S1 of X, Si of X, I from 1 to R, right? And then I take section S, which is just sum over Vi's Si. So of course its value at X will be P, and it is flat because these are flat. And so we are done. So S of X is P and nabla S is 0. So we are done by the theorem. Okay, so this is this corollary. I think we had 1 and this one is 2. Это константы.
То есть вот фиксированная точка.
Да, да, да. Но нам все равно какую брать, в смысле S какую брать, лишь бы она удовлетворяла вот этому. Вот. Не, ну она как бы и должна быть константой, иначе ну, вот это просто не будет выполняться. Да. Так, хорошо. Okay, so now our next goal is to obtain a little bit more known formula for curvature in the case when we have linear connection. And this will give us more statements actually. So if I have E now a fiber bundle which is vector bundle, and I have connection which is linear connection, then let me define, and again I identify at any point P of E, I kind of automatically identify in the formulas that I use vertical fiber of vertical bundle at P and fiber of E at pi of P. Because this is tangent space to fiber, and fiber now is vector space, and so I can have this identification. That was the whole point why a linear connection actually defines a connection in old sense. So from now on, linear connection is the same as like this previous connection, and I can sometimes write like this, sometimes write like this. It's all the same. Okay, so now let me for any V and W define the following map actually. So this is from sections of E to sections of E actually. So this is goes like this. So nabla V nabla W minus nabla W nabla V minus nabla corresponding to the commutator. Then we have the following theorem. So for any V, W, which are vector fields on X, S, which is a section of E, and X, which is just a point in X, we have. Okay, so what do? I take this R, V, W, act on S, get another section, compute its value at X. That's one side of equation. This equals 2. So now I take my curvature to form, which is over there, right? What should I do? I take omega H, apply it to V H W H. Okay, this vector fields should be in vector fields in E. I am going to to define what it is or remind because they already appeared in seminar list. And then, so okay, this gives me what? This gives me vector field in E, right? So what I do, I actually compute its value at S of X. This gives me vector in TE at this S of X. But this vector is vertical. So I can identify it with so this is this thing is an element in E which lives in the fiber of X, right? And this is this thing is in VE, right? In the fiber of VE at SX, and so I'm using this identification to write this equality. So hopefully it all makes sense. All right, so let us prove this. So proof is actually interesting, so it's not that obvious. First, I need to remind what is this. So if I have, so VH is a vector field on E, right? Defined by the following: VH at point P, P is a point in E, is a horizontal lift to point P of V at value phi of P. So so you have vector field V, and you lift it by horizontal lifts to vector field in E. Okay, and for W, of course, this in the same way. Right. So now we will use a couple of things that we need to recall. So proof. We need to recall the following. So suppose that I have nabla, which is a connection, like just linear connection on vector. So in this case, this E is just any vector bundle, not exactly the one that we. So we will apply it not to E that we have here, but rather to TE. So, but in our previous discussion, this was conversation about for any vector bundle. So if I have nabla which is connection on E, then well, what it is? It's a map, right, from gamma of E to gamma of E tensor T star X, right? But there is a map, so this gives me one form, right? But also I can like E valued one form, right? But I also can, by the same letter, I can extend it and this consider E valued, like a map from E valued K forms to E valued K plus 1 forms. So then we have a map which is like that. So if I have lambda K of T star X, tensor E goes to gamma of lambda K plus 1 T star X tensor E. So it's actually a generalization of D. Well, and it is defined. It was defined in the following way. So if I have nabla of omega tensor S, this is K form, this is section. This is defined as follows: as d omega tensor S plus negative 1 to the power K, where K is the degree of this form, omega tensor nabla S, something like this. Okay, we discussed it a little bit before. So I need to use this little bit more general understanding of nabla. This is one thing. And I claim that this being said, that if I take for any lambda, which is one form with values in E. So this is T star X, gamma of T star X, tensor E. So if I take this lambda and apply nabla to it, so I get two form, right? And two form knows how to eat two vector fields. So V and W vector fields on X. So this is two form, it's two vector fields. This will give me something, some section in E actually, right? And this equals to, so I take lambda and evaluate it at W and apply covariant derivative with respect to V to it, minus I take lambda evaluated at V, covariant derivative with respect to W, minus lambda of the commutator. Okay, this I will not again bother to prove in lecture, but this is direct general. So you have the same formula for D, right? And this is kind of just, you know, since nabla is a generalization for exterior derivative, it has the same formula. So I am going to use this.
Можно напрямую указать, если будет использовать определение.
Ну да. Не должно быть никаких концептуальных препятствий. Можно вообще это сделать там в координатах там как-нибудь. Ну, вообще так же, как это было, у нас было задание как бы на семинарском листе. Вот такое же доказать для D. Вот, это примерно так же делается. Вот. Okay, so now, I need, so this being said, now let me go back. So I have this nabla, right, in E, but this is not the nabla, what I'm going to apply this, not to this nabla, but rather to nabla tilde. So this is connection on the vector bundle VE over E. So actually VE is isomorphic to the pullback bundle with respect to pi. If you go back and see what is a pullback bundle, this is exactly what VE is. And so there is so I have connection on E, and what this is nabla tilde is what should be called pullback connection. So basically, it's the unique connection such that, the following thing happens. So it nabla d x p of v of some section at x is the same as nabla tilde of the pullback of the section S of V. So okay, let's see what's going on here and who is who. So my S, my S is a section of E. My V is is a vector field on E. Well, here I rather mean, so actually into this argument I can put vector fields, or just actually if I introduce a point where it is evaluated, I can put here corresponding tangent vector, right? Because this argument, nabla is linear with respect to this argument. That's why, right? So this is really V at point X, and then I apply dxp to it, right? And so this V. So rather V is a vector field on E, right? And here should be V of S of X, right? V of S of X. Right, what is P star of S? So this should be gamma of VE, right? So this should be a section. So for each point P in E, it should give me an element in VE. Well, I just take pi star of S at P is just the same as S of pi of P, basically. Well, we again, we need to identify fiber of VE and fiber of E. And therefore, this equality will make sense. Because, yeah, again, this should live in the fiber of VE, this should live in the fiber of E. Okay. So, anyways, I just claimed that there exists unique connection nabla tilde here that satisfies this property. Well, basically, how you can prove it, you just take some local basis of sections, right? You have some Christoffel symbols for this one, and then you pull back these sections, and you pull back like corresponding forms in which you write this down, and Christoffel symbols will be just the same, except like in vertical directions, they are just 0, and that's it. Oh, you have more indices in Christoffel symbol in here because the dimension is more. So the indices which are additional, we just take the corresponding Christoffel symbols to 0, and the ones that you got from X are just the same Christoffel symbols as before. So that's how it's done. Again, a lot of details, so if we will just look at all these details, we'll we'll never move on. So, but what we need is just really this formula. That's it. Okay, and finally, so I have this nabla, which I'm going to apply this. And what is this one form? So one form will be exactly this k. So my k, right, it's a map from sections of TE to sections of VE, right? And so therefore I can think of k as a section of T star, and it's linear in C infinity because it's just fiberwise projection. So I can think of it as this. And so, right, I take lambda, you see in this, lambda lives in T star x is replaced with E in this case. Tensor E, which is VE in our case, right? So my k is one form, it's really one form, right, from this claim, just written for this vector bundle. Okay, and so I just apply this claim to this one form, right? So where do I go? So I take two vectors, V and W. These are vector fields on X. I take them and consider their lifts, horizontal lifts. This live in vector fields of E. Then I take K and apply nabla tilde to it. And consider and evaluate it at VHWH. I applied this formula in claim. This will give me nabla tilde of VH K of WH minus nabla tilde of WH applied to K of VH and minus K of commutator VH WH. Well, these two terms are zero, of course, because this is horizontal and I project to vertical. Horizontal, I project to vertical. So this is zero, and what I get is exactly omega H of VH WH. Well, H doesn't do anything with these guys, right? It's projection to horizontal. They are already horizontal. And then I take commutator and consider K, right? And this explains why I have this minus sign at the definition of curvature. Okay. Very well. So what about the other side? Right, we had this, let me write it here. R VW applied to S. Right, applied to S, and I wanted to relate this at X. So, and this guy is nabla V, nabla W minus nabla W, nabla V minus nabla VW. So again, idea is that this thing is actually, this tensor doesn't depends only on values of V, W, and S at X. So this it's some computation, right? But this is actually linear if you in C infinity of x if I start multiplying s by it. And so actually I can plug in any other section that coincides with s at x and prove it. So here I actually plug something such that these two terms are 0. So to get the other part, I need to consider some vector fields such that this is 0. So the commutator of vector fields will be 0. So I will need some coordinates, because coordinates give me vector fields, commutator of which are 0. So that's the thing. Okay, so let me yeah, so we ran out of time, unfortunately. So I guess okay, we got what? We got that this equals to this. So let us remember that and start with this next time. Okay. Okay, let's have a break.